going to learn about the universe? How are they going to study the universe? Okay, before that, how old is the universe? Anybody? If you have listened to the introductory session clearly from your teacher, you'll be able to answer to this question. I can't hear you, dear. You're not audible. Are you speaking?
Okay, 13.7 billion years. 13.8.
13.7 or 13.8, you can say. Right? Fine. So, how are scientists actually studying about the universe? You can't see everything in this universe. Okay, not the same person every time. Others should also get chances. Come on, everybody. Answer to the question. Let's interact. How is it possible to study something which is millions of light years far away from us?
We can use telescopes or like satellites and rockets to like go on the moon.
Okay, that is just about the solar system. We are limited to travel in space. Telescopes also, it is limited. Space telescopes, basically. What kind of telescopes? Think about that.
What kind of telescopes?
Okay, good. Next, anybody else? Good job. Okay, the light with which we are seeing today is called as visible light, right? So you might have, seen your microwave ovens in your house, right? TV remotes, it works in some other frequencies. Everything works in different frequencies. That means different level of energies, right? So in this universe, we have 7 types of radiations. Have you heard about them? Gamma rays, X-rays, ultraviolet rays, visible light, radio waves. Have you heard about all of these terms? Say yes or no. I can see you. Do this or not? Yes, fine. Got it. Okay. So the pictures that are taken using Hubble Space Telescope, that works in visible light spectrum. Okay. You can capture the images of a very far away galaxy, by receiving the visible radiations from it. Other than that, we have heat coming from different parts of the universe, right? If you are observing the Triangulum galaxy, you take up the heat from the galaxy and generate the image. That is called infrared radiations. Then we have other stuffs, right? Ultraviolet, X-rays, gamma rays, everything. So these are the different types of radiations with which we use the process called as spectroscopy, right? It's the technique of spreading light into different components and study about them. Okay, so with respect to spectroscopy, we'll be able to find the different compositions of different galaxies, where they are, their positions, how far they are moving from each other, everything about them. Okay, it's basically their whole lifeline we can calculate and understand. Fine. Now this was the introductory session of what we are going to talk about today. Okay, so we cannot draw or take up the picture of the whole universe. Then what is it? What is this thing? The stuff. What is this then? How did we end up doing this? Is the major question today. Like, how did we reach up here? Why is this structure looking like this? Have you seen this image before in any of your YouTube videos or something like that? Yes or no? Yeah? What? Anybody, can you explain what is happening here in short? Not so lengthy.
Okay, so what is happening here is it's showing the Big Bang from now all the way back to 13.8 billion years ago at the start of it. It shows how it is expanding. It shows how it cooled down, and it shows how everything formed, like how.
Yes, great. Okay, so let's change or say something. You change up your mentality. Whenever you're talking about the origin of space, everybody will start, at a point in space, Big Bang happened. Now I'll say Before Big Bang, we didn't even have space and time. So how is this sentence even correct? The Big Bang itself happened at time equals 0. Okay, we didn't have time before that, we didn't have space before that. Okay, it's called as the cosmic singularity. What is it called? Singularity. A very tiny point of you unimaginably extreme, dense, hot point in this universe. In this universe, in the sense that was the universe. We can't say in this universe. Okay, so in physics, the word singularity indicates that everything that we know about the universe breaks down to infinite. So in science or mathematics or any physical scenario, we are not being able to imagine infinite, something called as infinity, right? So we are going to talk about a time. All of you are aware about exponents, right? Say yes or no. Exponents, 10 raised to something or not, right? Yes, you're big kids. Good. So we are going to talk about a timeline which is 10 to the power minus 3 seconds. That is basically 1 divided by 1 with 43 zeros. How much small it is. This unimaginably small, right? And everything till the first star was bombed happened in 1 second. This is 1 second. That is how fast everything was created by the Big Bang. Again, let me clear this fact. Big Bang theory is one such theory that is talking about how these things may have begun. We are not at all sure about it. Science is ever changing, ever evolving. Tomorrow they might come up with something else, right? Understood? People are working on dark matter, people are working on other stuffs. So everything that you study in science or maths or physics, it's ever changing. Nothing is constant, right? You might have learned about atomic theory and all, atomic models and all, right? Somebody told that it is just empty, then came nucleus, then came Rutherford, then came J.J. Thomson, and today we have atoms. Then atoms are indivisible. Atom is the basic building block of everything. Was that correct? No. Again, atoms are made up of electrons, protons and neutrons, and the nucleus, right? Again, what are protons and neutrons made up of? Anybody? This is the structure of an atom, right? You all are aware of it. Yes or no? Yes, right? Nobody's okay, fine. So what are, okay, protons, neutrons, and electrons are the components of an atom, right? Can anybody say yes or no? Are they indivisible? Are they made up of something else, or they are elementary particles? Elementary particles means that they are they. They are not made up of anything else. Anybody? Are they elementary particles, or are they made up of anything else, something else?
They are made up of quarks.
Yes. What? Electron, proton, or neutron?
All of them.
Think again. I'll give you 1 minute or 3 seconds, 5 seconds. 5, 4, 3, 2.
Like the ones that have minus and negative are made up of quarks.
No.
And neutron is?
No. Electrons are elementary particles, and protons and neutrons are made up of quarks. Now, when the universe began, let's move forward to the beginning. Fine. So this is basically the observable universe. As you can see, give me a second. This is basically, looks like an eye, a pupil. But yeah, this is how they have created the image of the observable universe. And let's move forward. Please go through the slide for 1 minute. Since it's completely an interactive session, I'm not going to concentrate more on the presentation. Yeah? Is it correct? Just go through. We'll talk about this thing later. Okay? CMB, radiation. Fine. Let's talk about how everything happened. Okay? So we know about the singularity, right? We talked about the singularity. Something happened. We don't know. Okay? Have you heard about Einstein's general theory of relativity? So it equations backwards in time. So it suggests a state of extremely high density, temperature, and it is described as singularity. Fine. So 10 raised to minus 32 second is the time, 43 second is the time, the maximum time we can ever imagine in the negative scale. We can't imagine beyond that, and we call it as the Planck time. Or this particular era, we call it as the Planck era or Planck epoch. So both quantum mechanics and gravity were equally important. Okay, so this is where we lack. This is why we are not sure right now to understand and make a theory called as quantum gravity. We need to merge these two subjects together in order to understand what happened exactly, clearly. Okay, so during this Planck epoch, quantum mechanics and gravity, the exact state before the Big Bang, was uncertain, and it is a very good active area in research right now. Okay, so quantum physics tells us that even empty space has tiny random energy fluctuations, changes in energy. We call it as quantum fluctuations. Okay, so during a hypothesized phase called as quantum inflation, the universe started to expand from this tiny dot. So again, I'll correct you. The Big Bang, as it suggests, as it means, is not an explosion, but it is an expansion. The universe expanded from a tiny point exponentially fast for a tiny fraction of a second. Okay, 10 raised to minus 32 seconds. That is the thing that is given here, 32 seconds. Okay, go through the slides also, in between. Fine. So this inflation explains why this universe, appears to be uniform on a very large scale. If you zoom out to the universe, completely, it appears to be the same everywhere. But there are a lot of voids here and there. You won't see anything there. It's just empty. So we'll talk about the emptiness when we reach here. Okay, we are just here right now. We have a long way to go. Okay, now during inflation, the temperature started to decrease. Okay, of course, if you are in a hot room, the temperature is boiling temperature, and I put all of you inside that room, what will happen? You start to run around here and there, right? What if I increase the area of the room? The temperature will decrease. What exactly happened there? The temperature is decreased. I don't mean to be from infinity it just came to 100 degrees Celsius. No, it was a very small decrease, but that decrease in the temperature caused something very beautiful to happen. Okay, the first fraction of a second where extreme energy processes started to convert those energy fluctuations into matter and antimatter. Okay, we have something called as quarks and electrons. So what are the basic elementary particles which were formed just after the Big Bang? It is quarks and electrons. Okay, you can call it as electrons and positrons. One is matter and other is antimatter. Now, one is positive, one is negative. That is the only difference between them. Okay, all the other factors are same. Mass, weight, everything is same. Fine. Not talking about weight, leave that. We talk about weight only where we are in Earth or something like that. Leave it. So whenever a matter particle and an antimatter particle are together, what will happen? Anybody? What will happen if a matter particle and an antimatter particle are coming together?
If a normal atom and an antimatter particle come together, they will collide and explode, neutralizing each other.
Yes, so they basically annihilate each other, right? And amount of photons are released. Matter, antimatter, they merge and become nothing. That nothing is basically light. 2 photons will be released. So at this particular moment of time, we had light. See, you can see in this image, right? There is light. Sorry for that. Okay, so this process produce a side of imbalance. Okay, so we don't know what is the reason behind. Okay, so the universe at this moment produced equal amount of matter and antimatter. So that means what? Everything merged with each other and produced just light. So why isn't this universe completely filled with light, and why are we existing? There has to have happened something there, right? We are made up of matter. We can't observe any antimatter around us, right? So where did this extra matter particles came? So we call it as asymmetry. A very small asymmetry must have been existed because every 10 billion, okay, 10 raised to 6 billion antimatter matter in exclusion or annihilation, we have one matter particle. Like that, the whole universe had a very, very small fraction of matter particles, and that matter particles created this whole universe. And we all are made up of that particular tiny fraction of matter particles. Is that clear? So we call this process as baryogenesis. I don't know if you have written that word here also. Listen to me clearly. It's called as baryogenesis. Baryon refers to the particles such as protons and neutrons, and electron is something else. Okay, they're not considered to be same, equal. Okay, photons are light particles in the early hot universe. Photons were abundant and constantly scattered off here and there, keeping the universe very much opaque and visible. Okay, now comes the next stage. We call it as nucleosynthesis stage, the forming of the first ever atoms in this universe, light elements. So within the first 3 minutes, okay, the universe cooled enough to allow something called as nuclear reactions. So this era is basically called as Big Bang nucleosynthesis. Okay, so during this period, protons, neutrons combined to produce light nuclei, primarily hydrogen or helium atoms. Basically, one proton is a hydrogen atom, two proton, two neutron is a helium atom, and very, very small amount of deuterium atoms. That is basically heavy hydrogen, which is having two protons. Okay, so the heavier elements, other than lithium, hydrogen, helium, lithium, only 3 types of things were present at the early universe. So heavier elements other than more past lithium require nuclear processes that happens only inside a star. So we haven't reached the stage at which a star is formed. Okay, now coming back to this point, I said quantum physics and gravity were working together. So what are the 4 fundamental forces in nature? Anybody? What are the 4 fundamental forces in nature? There are 4 types of forces. At the beginning of the universe, all 4 forces were together. We had one unified force, one grand force at this moment. What is it?
Gravitational force.
Okay, one. Then
Frictional force.
now. Good job. One is correct. The other 3 is left.
Magnetic force.
You have to add something to it. It starts with E. Dash magnetic force. Yeah, correct. Electromagnetic force. Very good. 3, third one.
Ma'am, weak nuclear force.
Yes, and the 4th one. Try.
Strong nuclear force.
Bus. Okay. So all the 4 forces. Very good. Good job, everyone. So all the 4 forces at the beginning of the universe were together, right? And the first force to get detached from the 4 forces is gravity. Okay, gravity is a force which is an attractive force between anything which has mass. Okay, electromagnetic force is the force of interaction. I'm not calling it as attraction or repulsion. It can be both. So I'm calling it to be an interactive force between anything which has charge. Okay, strong nuclear force, as it suggests, is a force which is binding the protons and neutrons together to form the nucleus. So the strong nuclear force is the basic force in nature, which is because of that we are having shape.